For summary part, basically propylene is produced by using on-purpose technology such as propane dehydrogenation (PDH) and metathesis. So the process description of propylene production has been described in details by using PFD, and we have been assigned a task to design a heat transfer unit, which is H105 splitter condenser, and below shows several steps that has been introduced in this designing process.
Brief process description. Firstly, the propane is pumped to the feed preheater. Then it enters feed heater to be heated through stream 9. Then the pressure is reduced to produce propylene and hydrogen. The product is then cooled, compressed, and undergo condensation and enter splitter condenser through flash drum. At this point, the distillate will undergo pressure reduction. The bottom product will be boiled to purge back the distillate, and the balance will be recycled back to the feed stream.
For milestone 1, we have 6 types of heat exchanger, where number 1 is H101, which is a feed preheater. Number 2 and number 3 heat exchanger is H102 and H103, which is a cooler. And H104 is a splitter preheater. Same goes to the H105, which is a splitter preheater also. And H106 is a reboiler.
In milestone 2, we are required to draw a block diagram based on the process flow diagram and label all the streams with temperature, pressure, flow rate, and all the component spaces. This is the block diagram with all the labelings. If we enlarge the heat exchangers part, this is the first heat exchanger with 4 streams, second and third heat exchanger with 2 streams each, fourth heat exchanger with 2 streams, fifth heat exchanger with 2 streams, and the final heat exchanger with 3 streams.
Okay, so now let me explain about milestone 3. As you can see, these are the conditions and the schematic diagram of H105, and we are working on it. In our design, lots of assumptions need to be made in order to proceed with the calculations. This table is used to approximate the heat transfer coefficient value, which we got it from Engineers Age website. This is the energy balance equation, and these are the assumptions that we have made, and a new equation is generated, and we are going to use this equation to calculate the outlet temperature of water. For a deeper understanding, the conditions of heat exchanger are shown again, and is very important and fundamental for further calculations.
For case 1, which is 1 shell pass with 1 tube pass, we calculate the log mean temperature difference and also the area of heat transfer. And from the area of heat transfer, we can calculate the number of tube and also the length of tubes, and which give us the approximate cross-sectional area is 2.78 meter square, and also the volume is 982 meter cube for 1 shell pass with 1 tube pass. For case 2, 1 shell pass with 2 tube passes, we need to use the Hoffman book to use the table 10 to determine the F value, which is 0.99, and this is the table. So same calculation with case 1, where we determine the log temperature difference and the area, so that we can find the number of tube and the length of tubes, and it gives us the cross-sectional area value is 5.56 meter square, and also the volume is 992 meter cube for 1 shell pass with 2 tube passes.
In case 3, the formula and calculations are almost the same as the previous one, but we have to refer to table 10.9 from Homer's book to get the value of F, as it's very important for the next calculation steps. After that, we may proceed with the rest of calculations.
In case 4, we use 2 shell passes with 36 tube passes. Since it's a shell and tube heat exchanger, we need to know the correction factor. In order to find the correction factor, we need to calculate the P and R value. After calculating the P and R value, we use table 10.9 to find the correction factor, which is equal to 1. The other part of the calculation is similar as the previous case. In case 5, we use double pipe, where fluid 1 flows horizontally and fluid 2 flows vertically. Since it's a double pipe, we does not need F value to calculate. We can just use Q equals to UAS delta Tm to proceed the calculation. The other part of the calculation is similar as the previous cases as well.
These are the types of popular heat exchanger and the types of flow that are currently used in industry, and we need to determine which configuration is suitable for H105. And these are the factors that we need to include too. After the discussion, case 4 is most suitable design for H105. So in conclusion, these are the results that we are obtained from the calculations. Unfortunately, in real industry, no assumptions can be made as the environmental factors and a lot of considerations that are shown need to be calculated in the design, as the outcome may be affected a lot if the design is calculated theoretically. That's all for our explanation. Thank you.